So this is an ongoing work, as you see here. And the main actors, beside myself, have been these people here. So Marco Piani was a faculty at Strathclyde when I was there. And Jacopo was actually my PhD student that now moved to ICFO. Then Neil was a postdoc for a year, more or less, before moving to IBM back in Barcelona. And Eric is a long-term collaborator that is at CISA and works on conformal field theory. This is more or less the outcome of the talk. So actually, there is a lot of overlap with what we have already heard. And again, it's about auto-equilibrium evolution, this entanglement barrier, and then there are a couple of suggestions on how we could overcome it. And actually, this trading entanglement trading entanglement for mixture rather than coherence. So using decoherence is very similar to what we have heard. Actually, it's actually the same. Whether the other part on using universality is a different twist. And everything here is at 0 temperature, so it's also a bit different from what we've heard previously. Okay, so I don't need probably to motivate it too much, but the idea is that if you move away from equilibrium, you could observe things that are not there at equilibrium. And I think that basically the main idea why we want to study system out of equilibrium, because we are in an era where we are trying to engineer kind of protected microscopic quantum effects. And we try to design material that have very specific properties. And sometimes equilibrium is too restrictive, right? For example, if you want a superconductor, then you know that you must be in a regime of temperature and magnetic field that maybe is hard to access experimentally. And this region of the phase diagram is really dictated by some equilibrium relation between energy, free energy, and entropy. And so you can't really go away from it at equilibrium. But maybe if you relax your request of being at equilibrium, maybe you can somehow obtain different things, right? So we all are very interested in auto-equilibrium physics. The question is that we really lack the tools. And so forgive me if I will be very, very naive and repeat what we have already heard 3 times. So if you want to sleep, I will raise a hand when I've done like 5 slides, because it's basically the same over and over. So let me specialize to a very specific setting. So that's the one of a quantum quench. So I have a ground state of an Hamiltonian. In my case, it will always be local. And then I take that ground state, change the Hamiltonian abruptly, and let the system evolve using our standard Schrödinger equation. So my system now, it was in a state psi 0 that was shortly correlated because I had this local Hamiltonian. And then it evolves, right? And if you look at it, nothing really happens. You need to look at correlation to see that things are going on. So for example, this is a kind of 2-point correlation function. And you see that there is a lot of structure of things going on. There is obviously a kind of Lieb-Robinson cone, but there are other features that can emerge. And the question is, how can we study the things beyond several times that are of the order t times over hopping, or of the order 10, 20 maybe. That's what we typically manage to do with the MRG, right? And so why do we have to stop there? So let's just review it fastly. The idea is that if we have product state in our tensor language, you have these 2 states that you can completely describe independently. So there is no problem. You can describe them independently, maybe even decompose them as how do I go back? I keep going forward. Oh, yeah, there is a different button. Sorry. Because this is too big, I thought he had several corners, but it's just one button and another button. Sorry. Okay, so here
I can decompose it as a tensor network, even if I want, right? The point is that there is no correlation. And as soon as I don't have a product state, so here you see I have a sum, then I start having correlation. So I have several states here, so I need to put a leg. I didn't explain really this notation, but I hope everyone knows. So a dot is a tensor, the legs are the indices. So now you see that I have these indices, so these legs join these two big balls, and this is this index here, right? And this index here is, if there is one, then more than one value is telling me that now I have a kind of non-product state between A and B, okay? And obviously this is a picture taken from one of Giffrey papers, I think. The more indices I get, so I can get more entanglement or correlation by either increasing the size of my index, one single big index, or putting several small indices connecting the two bipartition, right? So it's kind of so we have a region A and the rest is B. So here I have just one leg, and here I have several legs, and then this increases the amount of correlations that I can have between A and B. And then it turns out that, as we all well know, you can upper bound the entanglement with the number of actually these legs that connects A with B in a tensor network. And for those states that are kind of organized like that in a real space pattern, you immediately see that the number of legs that connect A with B has to do with the perimeter of the area or the area of the region A. And so we say that these states somehow, if you keep a fixed bond dimension, obey an area law. And the reason for that is this, right? That the number of connection increases with the perimeter, so they obey an area law, and then you can have different things also. But the question is now, let's go now to the out of equilibrium dynamics, and then obviously I didn't say that, but the larger the entanglement, the harder typically is to describe the state in a naive way, right? It becomes more and more complex. Because somehow your tensor network contraction depends on the legs that you have to contract, and then if you have to connect more legs, it becomes harder, typically. Okay. So now let's go to the out of equilibrium situation, and this is one of these quench I was mentioning before. And here on the x-axis you have time, and in the y-axis you have entropy. This is entanglement entropy. There's a measure of correlation again. And what you see is that, considering different system size, what happens is that this entropy always grows linearly in time, and then it saturates. But it saturates to a value that is proportional now to the length of the system, right? So it's a kind of volume law saturation. And again, keep in mind this picture, because it also tells us that not much is going on after saturation of a certain block, right? So we have large blocks, and each blocks equilibrate, if you want to, at a different time. But once this has equilibrated, nothing. There is some. So if you look at the really horizontal line, it's slightly different from what's going on here. So there is still some slow things coming on. It's probably a lattice artifact. So if you would do kind of a continuum theory of these things, if there is such a thing like a continuum limit of this lattice model, you would probably see a kind of two straight lines that kind of have a discontinuity. The presence of the lattice induces some effects that can be described here by this kind of rounding thing. But now, if you follow this entropy, so we say this entropy grows linearly in time. We had this formula here. So we use, for example, matrix product state. So we only have two here links. NAB is 2. So we have that the entropy grows in time, meaning that this bond dimension squared, if you want, must be larger than the exponential of the entropy, so exponential of time. Okay, so that's the origin of what we say exponential hardness of simulating out of equilibrium system with MPS. Again, I stress with MPS doesn't necessarily mean with tensor network, right? That's with MPS, so it's very important that we keep that in mind. Okay, so how do we go for an improvement. So if you're Giffre, you design a new tensor network, probably it's called branching Mira, you would like to try that out of equilibrium. Giffre, why haven't you tried that? But anyway, so there are ansatz that have volume law entanglement that are polynomially contractible, so that you could still do calculation in the polynomial time with those ansatz. They haven't been used, so I don't know if their structure is actually the correct one to describe quenches. It smells like it is, but they haven't been used. If you are me, then you do a different thing. And the idea is that you try to find a physical mechanism that would somehow, is so robust, that would somehow drive your result towards the correct thing, right? So that's one of the goals that I'm pursuing. And then the other one that is very, very similar actually is possibly the same intuition that everyone else has discussed today. You kind of use this idea that I already mentioned of local thermalization, right? So thermalization seems to appear locally at different length scale, and then you can try to somehow, after some time, trade your entanglement for mixture, and this is also another possible way of going, right? And that's exactly in the same direction that we have already heard. So I will try maybe not to spend too much onto that because it has already been described, and there are several recipes. We had one slightly different from the previous one that we heard, but that's really the same spirit. So let me go into the thing that I think is a bit more original, what I'm trying to do, that is this universality idea, okay? So when did we had such an example? Well, first let me define what I mean by universality. Actually, universality means that there is some what we believe as a critical point where correlation decay algebraically rather than exponentially. And everything is described by a very small set of parameters that are the critical exponent. Several models that are different have the same large distance behavior, so that they can be organized in class. And this class have several data, but at very raw level, we can just characterize them by the critical exponent. So obviously, that's not enough, but it's important to for the moment simplify to this level. And it turns out that in particular, if these critical systems are also conformally invariant, then the same critical exponent appear in finite size spectra. So if you want the low energy spectra, once you regularize the theory on a finite geometry, encodes the same exponent that you see in the things. And so seeing some kind of regular structure in some energy spectra is equivalent of seeing some smoking gun of a critical point. Okay, so that's a bit the philosophy of what I'm going to describe later. Why is it important? Well, we had already an example in the case again of critical systems. Critical systems don't fulfill the area law. Their ground state has what are called logarithmic violation to the area law. Again, these were computed in the 90s, and then there is this famous paper by Giffre in which, so this picture is actually taken by, sorry, Giffre. It's an old slide, so. and then here you can see that if your Hamiltonian has a gap, then the ground state. So here you have the sides of your block, and then the ground state entanglement saturates at what we call the area law. But if your system is critical, it keeps increasing with the logarithmic increase. And then obviously this is not the place in which you want to use simulation with matrix prostate with fixed bond dimension, because again the entanglement would saturate at the log of that bond dimension. Nevertheless, if you try to do that, and I think that Andreas will talk more about that, so here is what happens if you insist of doing that simulation. So this black line would be the exact result if you were able to kind of, if you scale your bond dimension. So here I have the system size in the x-axis. In the y-axis, I have the error of the energy with respect to the infinite case. If I only using kind of rings of increasingly large size, then there is an analytic prediction that is this 1/n² correction that is in this log-log scale is just a straight line. This would be what the exact simulation would give me. Now, if I do matrix prostate simulation with fixed bond dimension, that again, they are kind of wrong,
I follow this prediction for some length, and then I completely deviate. And then you see, I get some results that only depend on the bond dimension and not anymore on the size of the system, right? And if you plot the inset of these things, you realize there is kind of some emerging scaling. And this emerging scaling can be used once you realize that this emerging scaling is equivalent to an effective correlation length. Then you can use your finite correlation length scaling that it has been used in Monte Carlo for most of our lives, in the same way you use finite size scaling to kind of extract the critical exponent of the theory. So even though your system is never critical, you use this scaling analysis as a smoking gun of criticality, and you extract the information there. And now you can do the Olympics, which is the most precise way of doing these things. I don't know. Actually, that typically gives you an idea of what the critical exponents are at a good enough level to kind of typically identify some universality class. And the picture is this one. So you have an RG fixed point. You are trying to locally, at least in the equilibrium case, you are trying to locally minimize the energy. So by locally minimizing the energy, you get close to that fixed point. Then you are making some approximation. So this approximation means that if you're close enough to your fixed point, you can kind of diagonalize your RG transformation, and you get a relevant and irrelevant direction. And most of the times, you can't guarantee that you don't pick a relevant direction. And so your finite bond dimension just has a kind of finite overlap on the relevant direction. And then by tuning that, you move along this relevant line, and you can, again, using typical scaling analysis, extract all the universal information. So this is just to mention that it would ideally would be great to find something like that out of equilibrium, right? Some kind of fixed point that I could kind of get close to with my matrix product state, for example, with finite bond dimension, and then just extrapolate the results. And so this brings us to our first kind of ingredient of that. In order to do that, we have to find this kind of fixed point, right? Where do we find this fixed point? So this is a project that we kind of did with the three gentlemen here. Again, Eric, Tony is at CISA in Italy. Jacopo was my PhD student at the time, and Neil was a postdoc working with us. And the results are published here in these two papers here. So what we discovered that actually become critical is not the Hamiltonian in this case. So it's something that is still, it's related to the state. So it's a kind of different criticality. So actually at equilibrium and out of equilibrium, the two things are related because of, again, this conformal symmetry. So it turns out that once the Hamiltonians become gapless, there are also other objects that become gapless in the same way that we showed before that somehow the correlation function exponent is the same than the level spacing in a finite size. So there is a similar reason that tells you that if your system has conformal invariance, also what is called the entanglement Hamiltonian, that would be the logarithm of a reduced density matrix, become gapless, and the spectrum also encodes the same universal exponents. Actually, this was first observed numerically again by Andreas. I hope I have, yes, because this I think is a fantastic paper also. So Gifrey, you see, I don't only. So yes, so this is exactly this entanglement spectroscopy analysis in which Andreas kind of plotted these entanglement levels as a function of 1 over log of the block size. And you see there are very strong corrections, mainly at higher levels, but there is a clear match with what you would expect from the spectrum of the Ising model. In this case, there is again these dotted lines here, okay? And you can find his paper online. And so the message is that, again, thanks to all this extensive conformal symmetry, you can actually then, later it was proven that that's actually the case by again, Eric Tonney and John Cardy. There were independent papers, and is again a result of this machinery of conformal mappings in which you can map different operators one to the other thanks to these things. And there is also a kind of mirror version of that on the lattice. So you can be safe that it works also on the lattice. Now let's go. So this is at equilibrium. Let's go out of equilibrium. And again, here I discuss three different scenarios. Why do I distinguish this different scenario? Well, because it turns out that a very naive strategy to perform out of equilibrium simulation is just to perform Euclidean time evolution and do an analytic continuation of your results. And in principle, there is no reason why it shouldn't work, unless you have what Anatoly Polkonikov, Marcus Hale, and Karen define as a dynamical quantum phase transition, in which if you look somehow at the return rate of your wave function after some time evolution, you would see that there is a kind of generalization of line of Fisher zero in the complex plane of the time. So time can become complex. So you have real time and imaginary time. And then once you quench across, at least once you quench at some places in your phase diagram, and originally the conjecture was that it was exactly once you quenched across a kind of equilibrium phase transition, and then things have changed a bit. But there are situations in which clearly you see this coalescence of Fisher line zero, and so you clearly cannot do the analytic continuation. Okay, so that's really one of these cases in which you expect that there is some kind of complexity barrier, because there is some non-analyticity in going between real time and imaginary time, so you can't do analytic continuations. And so what I want to propose here is a different characterization of the DQPT, so dynamical quantum phase transition, not in terms of this non-analyticity of Loschmidt equals zero that have been used previously, but in terms of these asymptotic properties of the state. And so here, this is something I did a while ago with Giacomo Torlai and Gabriele Di Chiara. And the conjecture there was that actually I could see again this DQPT by checking what was happening to my entanglement spectrum. So if I wouldn't cross the DQPT, you see that my entanglement spectrum, so such in this first panel here, so here, sorry, you have times versus Schmidt values, right? So I have the Schmidt values of a bipartition. I think here was half of the system. And again, this is a plot for the Ising model. So I'm quenching from transverse field 1.5 to, for example, in A 1.2. So I'm in the same phase. And you see that what happens is that the entanglement spectrum stays gapped. Okay, so there is nothing special going on. There are some levels coming up, so the complexity increases, but nothing really goes on. Now, if I quench across the critical point, right? What you do see at kind of large time, here again is a free Fermi calculation, so I can go to larger time than what I would be able to do with the MRG. You see that there is a pinching of this spectrum, right? All the levels start to get together, and interestingly, so if you go from one side of the phase diagram to the other, you don't see any strange non-analyticity. Whether if you do it in the other side, you do see a strange non-analyticity that actually whose times actually coincide with this non-analyticity of the Loschmidt echo. So it's a kind of a pinching so there are two Schmidt values that are kind of oscillating one with respect to the other, and there are some times in which they cross. So these are these non-analyticity of the Loschmidt echo. But what I insist, that to me is not really the manifestation of the DQPT, because in one side, so quenching from one direction to the other, I see it, whether in the other direction I don't. What I insisted to me is manifestation of the DQPT is this fact that the entanglement Hamiltonian is becoming gapless in the long time limit. Okay, so you see, independently on having pinches, so all these oscillation, or having just very smooth stuff, these two objects are really becoming gapless because I have crossed a transition, or I have also quenched maybe exactly at the critical point. At least in the Ising case, these also work. Okay, but this was so this was published after Andrea's paper, but I never kind of realized that this could, so that somehow what you were seeing at equilibrium could have some consequence also out of equilibrium. So at that point, I just had this conjecture that the Schmidt, so the entanglement Hamiltonian would become gapless, but I never thought, what is the spectrum of that, right? So this was just kind of an observation. Then there was Andrea's paper, then there was John Cardy's paper with Eric Tony, and then I kept thinking about it, and I decided to revisit it after all this paper. And now I'm plotting the same stuff here, and I want to focus on the fact that now we have a finite system. So you see, I have these phase one. So you have to read this plot is again times over L. So L is the size of the bipartition. So there are several system sides all on the same plot, but it doesn't really matter. So what you want to read is on the right is the scale of the entanglement entropy. Okay, and is this dark curve here. So you have again this linear growth and then kind of thermalization or equilibration if you want. And then this phase 3 is just a finite size effect because I'm on the ring. So the things come back. So the entanglement entropy goes down, then it goes up again, and so on. Okay. So region 3 is a finite size effect. What you are interested in would be region 1 and region 2. So if you had an infinite system, region 1 would extend, and region 2 would be your equilibration, right? If you look at the finite block, you have still an equilibration regime, and then it would never come back, basically, if the system were infinite, right? The fact that it comes back is just for finite. So this is the line of the entropy, and this is the line, again, of the Schmidt coefficient, right? So you see, again, they are becoming gapless. So, but you start seeing here, if you look carefully, that there is some structure to that, right? So you can see that there are kind of very regular things. And then how do you extract the structure? Where you just compute the ratios, right? And that's amazing. If you compute the ratio, nothing is going on, actually, right? Yes?
Can you go back to the previous slide?
Sure. Yes.
So what do you mean by gapless here? Like there's a lowest thing which seems to be separated by a gap.
Yes. So
the higher lying things.
Yes. So what I really mean is that if I had a larger system, right? These things here is the entropy that you have to read on the right scale.
Oh, I see.
And these color stuff are the eigenvalues that you have to read on the left scale.
Ah, okay, sorry.
And then yes, what I'm interested in here is the gap here, right? And what I'm saying here, there is just a finite time effect. So if I had an infinite system and I could wait infinitely long, then these things here would just become 0. The thing that I have a finite system, then at some point it opens again and it comes back. Okay,
and the subsystem you're considering is always half the chain?
Yes. So here indeed, so it's 1/4 indeed. But yes, so I'm morally trying to go into the continuum limit in which I really take larger system and larger block. So it's not local in a sense, local observable. It's really kind of continuum system, continuum limit of a subpart of the system. Okay. Everything clear? So okay. So again, so once we saw this, there is a short time prediction from CFT. So I didn't put the things. So the short time maybe was not so surprising because there is a CFT prediction. And if you believe in thermalization, there is also a thermal prediction. So somehow there are two predictions. But the fact that they completely match, so there is nothing going on, it's amazing. And actually, it's even more interesting if you, so this is a kind of a block at the beginning of the system. If I would have put a block at the middle of the system, there would be kind of a shooting here. So you can look at the data in our paper. So there is a kind of rearrangement of the levels once the system equilibrates. But you see, I would like to pause a bit because this really looks like, at least from a point of view of the spectrum, it's not that there is pre-thermalization, it's that nothing is really going on, right? So it's really like the same spectrum is just being shifted with time, by a prefactor that has to do with how long I wait, right? The more I wait, the closer the gap the smaller the gaps become, but nothing else is going on, okay? And so this would be a kind of so this so I forgot to mention. Everything I just said is for the quench exactly at the critical point.
And here, exactly at the critical point, as I mentioned, you can have some CFT prediction at very short time, some completely independent CFT prediction coming from a kind of thermal state if you believe that there is thermalization. But we know that this is a system that is integrable, so in principle there is no thermalization. So there are several things. But what is also, I think, remarkable, and it's one of the results, is actually it doesn't matter if the system is integrable or not, because if you look in this continuum limit, and here I've plotted in red the spectrum of a generalized Gibbs ensemble, that it's very easy to get with the free fermions, because it's just the ensemble in which you keep your free fermion occupation constant. So you have all the fermionic mode that need to be conserved because it's a free system. And you plot the spectrum of the Gibbs ensemble, and then as you increase your block size, so these are now reduced matrices of these two ensemble, and you just diagonalize it. As you increase the block size, you see that they go one onto the other at low energy. So it's really the fact, at least my explanation is that I have a kind of pseudo-local object, right? This entanglement Hamiltonian is a pseudo-local Hamiltonian because it has a long tail, exponentially long tail, but it's a kind of pseudo-local object that is becoming gapless. And then due to universality and Z2 symmetry, there is just one critical point, right? So it doesn't matter if it's GGE, if it is Gibbs, it doesn't matter if it becomes gapless. That's the spectrum that you get, okay? So I think it's a very strong message that no one really kind of got from our paper, but I would like to stress it. And it's also important because that somehow, for those of you that have been around I'm kind of a CFT amateur. I'm not an expert of CFT, but there was always this debate in which if you do acto equilibrium with CFT, you always get thermalization, right? Whether people know that the integral system get generalized Gibbs ensemble, and then there are a series of papers of John Caddy in which he would explain, and I think Jérôme Dubail also started discussing with Stefan also at the paper in which they would suggest possible ways out of it. But at least in this case, it seems that really the CFT is all what there is, right? Even at least in the continuum limit, obviously. Okay, so on the lattice things are different. Okay, so this would be, yes?
Can you remind me what L, small l is?
Is the size of the block?
So
Yes.
the system is
Yes. Here, exactly, and I'm kind of, no, sorry, actually the system is 4 times small l. So,
large enough.
yes, but it's important that you grow the system size and the block size at the same time because you want to go to the continuum limit. If not, you would go to the thermodynamic limit on the lattice. It's different.
And that's where you see the...
Yes, that they correlate, yes. Okay. Okay, so this is again smelling of some kind of possible use of universality out of equilibrium, right? I don't have still an answer on how to actually use this critical point in the entanglement spectrum to make scaling, but it seems that at least there is a kind of a correlation line that goes to 0 that one could try to use to scale stuff in the same way we did with the MPS. Now there is a small surprise in as soon as you try to do something in which you can't use free fermions, and the 3-state Potts model is the first example that we tried to address. I mean, it wasn't the pandemic, so I could only use my laptop. So that's one dimension I could use, right, in these things. So I'm pretty sure that if I mean, 2 days ago I had a talk of someone using bond dimension of 4,000. So I'm humiliated by that. I'm sorry. So this is just 800, and but you have to think that it's a finite system. Maybe it's the same for you, but this is a finite system. So I think this was kind of already 200 or 300 sides. So I have 300 times matrices. So it's not IDMRG, right? It's finite size DMRG. So there is a factor there coming with the number of sides. So things scale. But anyway, it was my laptop, so I can't complain that much. Okay, it was 64, sorry, but I think I also have data for 120. But so what you see here is actually there are very strong correction again for finite time. And then what you see here in the dotted lines are the spectra for what we believe from Andreas' analysis should be the correct boundary condition for the Potts case, and for Ising it would match perfectly. But here you see a new level coming out. So what I just said, that there is kind of an operator becoming gapless, this is still true, right? So the entanglement spectrum become gapless. It's just that the universality class seems to be different from the one that you get at equilibrium. And now, is it indeed an effect of now GGE being different from Gibbs? Because again, Potts here, it's integral again. I don't know. So we have many speculation. Again, there was the pandemic. Neil left for IBM for better salaries and life. So this is something. So this is something that is still something I would like to work more on to understand where this spurious level coming from. It seems to have a lot to do with the things that Frederick Mila and Natalia Cepiga have been doing about non-commensurability in these Potts things. But I don't want to say things that I actually didn't check. But definitely, so there is still a universal spectrum. It's just not the one. So there are a lot of correction. You see, things don't really necessarily scale as well as the Ising model. The Ising model, we had several sides, and you could see almost only one line. Here you see different sides and different partition kind of don't necessarily overlap. These lines, again, are the regimes, right? So this would be regime 1, regime 2, and regime 3. So it's a bit different from what happens into the Ising case. And the question is just because in the Ising case I was using 10 times larger system and 10 times larger times, right? Is it just a finite time effect that I could kind of reach because I had the free fermions and here I don't? Or is there something new in this critical point? And I can't answer the question right now. But definitely there is still an object that is becoming gapless, it's just that we don't completely understand the spectrum. You see some of the levels are there, some other are not. Okay, so this is the end of the first part. Are there any questions? On to, yes, Max.
Just to clarify, on where would be DQPTs on your plot, right? So you rescale time by L on the previous Ising case.
Okay, so
DQPTs are not visible. If there would be DQPTs, there would be squished sort of towards zero.
Yes, so sorry, exactly. So in this plot here, if you just do the quench in one direction, the DQPT is exactly at this crossing of the entanglement spectrum. I hoped I had a slide, but I didn't put it. So actually, you can repeat the same plot here. So this is just at the critical point. So I still didn't cross the DQPT. So I could repeat the same plot for a quench in which I would cross the things. And you would see a very similar stuff, but with a lot of, again, since you typically normalize by the smallest, so you divide by the first, you see, these are the entanglement gap divided by the first. When the first diverge, then you see kind of very much numerical instability. And so you would see the same stuff, but with a lot of noise. So you can look at our paper. There is the plot there. And that is very interesting because there is absolutely no CFT prediction for that. But you see, with this extra caveat that there is this noise coming from the touching of the levels, right? So that we normalize, you divide by infinite, and then so you divide by 0, and then it goes to infinite. Everything goes there. When there is not such peak, you see the same level structure. And
maybe we should discuss after the talk. But basically, for the first two eigenvalues, if you write your MPS in a Vidal form, we have an analytical prediction for early times.
Yes.
So there is.
Yes. But again, my message here would be that you probably are well aware there are two definitions of DQPT, right? The one of the 0 of the Loschmidt echo, right? And the one in which you define a DQPT when you start from an ordered state and you ask yourself, when I quench the infinite time state, is it still order or disorder, right? And then depending on your parameter, right, there is a critical parameter in which after you pass that parameter, then the state disorders. And then kind of the Silva, if you want, definition of DQPT, right? So there are, So I'm more in that spirit. So I'm more in the spirit of watching the kind of infinite time limit and see that these entanglement spectrum become gapless, rather than fixing the T stars at which these crossing happen. And there was maybe there was a bit the message in this slide here. So you see on these sides you see this quenching and you see this non-analyticity. On this other side, so you quench in the other direction, you don't see anything, but still at a long time the entanglement spectrum is getting gapless. And this is the feature of the from me is a feature of the equilibrium state, if you want, rather than at finite time. So it's a slightly different perspective. I know it's not the standard one.
But again, the entanglement spectrum getting gapless, it's not a signature of thermalization, volume law entanglement in some sense, or is it?
No, I think
is
so.
it the wrong language?
Thermalization is still there here. So even if the entanglement spectrum is gapped, because the thermalization is just telling you that your state is a thermal state of an Hamiltonian. What I'm trying to say is that this Hamiltonian is becoming gapless at the DQPT. So you're at finite temperature. So that's basically, I think, the message. You're at finite temperature, so you don't see really a critical point. You see a critical fan, right? Because you are at finite energy density that I translated to finite temperature. But the Hamiltonian is becoming gapless. And so since the Hamiltonian is becoming gapless, there are still signs of this zero temperature phase transition. So, and that's why you see it in the Loschmidt echo. So you don't see it inobservable, right? Because it's a zero temperature stuff, and you are at finite temperature, but you still have a kind of critical fan. And that would be the things I would like to exploit to do kind of long time dynamics using scaling theories. So that would be a bit the strategy. Okay, sorry. I was slow in answering the question. How much time do I still have? Okay, but anyway, the second part is the older thing, and it's very, very, very is the same of all the other approach that we heard, right? The idea is, again, focusing on this plot here is, again, that different length scale thermalize at different time. So, and that's something that until very recently is not being exploited properly, right? And since 2000, I think the first one was actually this paper here, right? 2017, I think we started to try to exploit that and find things. And so what we tried to do was, so our thing is slightly different, but I think it's small nuances. So, and let me maybe justify it a bit more. In quantum mechanics, you have coherence, right? Coherence manifests itself in the fact that particles are also wavy if you look at them close enough, right? But at finite temperature, you have let's say, once your de Broglie length become or if you want your particles are sufficiently separated with respect to the de Broglie length, then you can just use classical theory, right? There is no sense in using quantum mechanics, and this defines actually the Broglie wavelengths that depends on the temperature, and so the idea would be at very short distance I would like to keep coherence, but at large distances I don't care, right? I just use classical stuff or decohered things, right? And I think it's very, so what I mean about coherence, sorry, I didn't define it, but so if you have a density matrix, you can write it like that, and these are some intrinsic uncertainty due to the fact, an extrinsic uncertainty due to the fact that you have a probability distribution of states. But then if that state, this particular state is not an eigenstate of an operator, even if you were absolutely certain about which state you would still have a variance coming from the fact that your operator doesn't commute. So your state is not an eigenstate of that operator, right? Or say in other words that your density matrix doesn't commute with your operator. And then this is a notion of coherence. Whenever this doesn't happen, so whenever your operator is co-diagonal with the density matrix, then you have an incoherent state, right? That can be treated basically classically because you have a probability distribution, right? That you can. Okay. And so let me try to motivate why that's the case. Again, in these simple integrable systems or systems in which you can somehow you have translation invariance and then momentum is a good quantum number. And then at least if the system has this pseudo-particle excitation, and in most of the cases we used also spin wave theory, so you can kind of get very good approximation by very good prediction by very brute force approximation. You can define kind of energy momentum dispersion relation. And then your excitation somehow would have could form kind of wave packets around some momentum, and they would spread with the what is called group velocity. That is just the derivative of your dispersion relation. And so if you believe in this picture, so that you kind of can describe the excitation by this, if you want, even at spin wave approximation, then what happens is that locally, so this again, I think the first insight on that was by Card and Calabrese in 2005. Locally, you have this population of excitation, and if your state is shortly correlated locally, then these excitations start to spread with this velocity. That depends again on the dispersion relation. Some of them are right mover, some of them are left mover, so they spread and they radiate the correlation at longer distance. And then the thing is that, so that's the picture in terms of this pseudoparticle. If you look at the block, now pseudoparticles that are correlated, so the blue one are moving on to the right and are correlated with the one on the left, so are starting to fill your blocks. And at some point you arrive to a kind of an equilibrium, things like an exclusion process in which you have a steady current of right mover and a steady current of left mover, but they are all correlated with things that are very far apart. And so this would be the kind of pseudoparticle picture of this equilibrated state, right? And then obviously the smaller your block, the shorter is the equilibration time, right? But that's more or less what happened. And again, this later onset of the entropy has to do with the spread of your velocity. That obviously is a lattice artifact, right? At least in a kind of CFT scenario. And so what is the proposal is very similar. So you start with a pure state, you evolve it, and then at some point you decide that your pure state you want to just approximate with the mixed state. Here you see it's slightly different because we have this purification, so we ensure that there is no non-physicality in the things. And what is your cost function? So you start, for example, from a very simple ansatz in which you say, okay, my system has thermalized, so this is just the reduced density matrix is just the thermal state of your local block, and then you just variationally minimize the distance between these two guys, right? And then once you've done that, you have a mixed state, and now you reiterate the evolution on the mixed state, and again you keep going and try to do your thing. So what we did is we tried to test it on Gaussian state, because there you have a lot of control, not only on the entropy, but also on how it distributes. It's called something like entanglement contour. I don't want to go into the detail, but the main working horse are these correlation matrices. And then the idea is that what you would like to do is you want to kind of find this band structure in which everything is well approximated, and then you want to, so you diagonalize your reduced density matrix in the block, and you want to transform entanglement by mixture. How you do that? You erase coherence. So you erase the correlation between your modes that are in the block with the one that are outside the blocks at a certain distance that is larger than some things that you want to protect, right? This is the same things that before we heard, that you have some blocks that you want to protect, so you have some support of your reduced density matrix that you don't want to touch, and you want to transform entanglement into mixture by erasing parts of the correlation matrix that is farther apart from that. And here, just to give you an idea on just a local observable, so here it's a bit busy, the plot, but there are several things. So there is a very short system, so 20 spin, in which you didn't do any approximation. You see this m would be this distance from the diagonal after which I would kind of erase coherences. Then there is an intermediately long system, and then there is a large system with 1,500 spin. And again, these are all somehow exact. And then there is our methods applied to a system that only has 200 spins, so it's relatively small. But we only kept the coherence up to distance 20, right? And so really the cost of this method is the same that the cost of this method here with 20 spins, right? Because we kind of use very small correlation matrices that are 20 by 20 and just keep adding mixed state into them rather than things. And then you can look at the exact evolution would be the thermodynamic limit is this blue line here. So you see it oscillates a bit and then it just stays there. And now the finite size 20, you see it's a mess because it constantly so correlation constantly bounce from the boundary and come in and out from your local operator. The 200 is getting very close to these things, and then again it has this recurrence, and then again it becomes a mess. And our green things, you see something in between, right? It gets very close, then it has this mess, but then again slowly it stays very close to the. So you don't get this bouncing mess of the red one, right? So it stays. It's not exact, so there is an approximation obviously, but it stays very close to the exact result at the same price. So this is a message, but I think it's very similar to what we have already heard. It's just a different way of seeing it. And then you can ask yourself how things decay in time, and is the exact thing, and then there is approximation. You can find some exponent that describe how well things are. So you can read the paper, but the message is really the same. Okay, so I just conclude by saying that I think that there is a certain amount of evidence from very different perspective. Also, this transverse contraction that Mari-Carmen and Banyuls and Dima Abanin are working on. So there are several perspectives that are kind of converging to the fact that I think we will be able to, in the near future, to circumvent this entanglement barrier by using different things. We definitely, part of it is definitely to understand better the physics and understand where the complexity comes from. Is it from entanglement? Is it also from coherence? Can we actually use this advanced tensor network that have been proposed several years ago to kind of encode the correct structure? And in this talk, I focus on the possibility of identifying some universality things and critical fun, and the coherence as two main ingredients that we could input in our next generation tensor network algorithm to perform long-time evolution of quantum system. Okay, thank you very much. Thanks.
Okay, I just had one which was about, maybe it was already asked in a different form, but when you were talking about this spectrum becoming gapless and then matching, CFT predictions, is that something where you could do a kind of scaling depending on like how far you quench from when you quench from different distances from the critical point? Is it possible that there could be some kind of universality in that distance?
That's a good question, because this would amount to adding an extra relevant perturbation. So I think in the system there is already one relevant perturbation, that is time. So the infinite time limit is gapless. So in the same way in which finite size systems are gapped and infinite size systems are gapless, here we have finite time system are gapped, and infinite time system are gapless. If you quench at or across the critical point. So this is the thing. If you quench close to the critical point, then you're again putting an extra scale that is so if you quench before the critical point, you're putting an extra scale that is again probably an extra relevant perturbation. But we tried to analyze that, but we didn't really understood how this extra. So we tried to analyze the non-critical quench in terms of the critical one, but as far both from the CFT point of view, because you could try to do it from the CFT point of view, it requires higher order correlation function, so it's not easy, but also from the numerical point of view, and we didn't really manage to make sense of it. So we have to, and I think that is related to the fact that you're not at zero temperature, so you are really at finite energy density. So you would like that distance from the critical point should be small with respect to, so to study it in terms of the fixed point, you should be kind of, if you want, a smaller perturbation than the one that you have already from the temperature. Again, I think we didn't put too much effort into that because it didn't come out immediately. So I think there must be some. I mean, if that doesn't work, it's difficult to make any other thing work in terms of scaling. So it would definitely be something to understand.
Okay, thanks.
But the scaling thing is the time here. Is really so you have to scale in terms of time, and this kind of finite gap in the entanglement spectrum that is due to the finite time. So this would be the possible scaling, the equivalent of a correlation length, let's say, or size of the system.
Great. Okay.